basically, my problem was called Candy 7. And basically, there are n friends with each of them having a piece of candy, and find the total number of ways to distribute the candy so that everyone ends up with one that isn't their own. And if you're familiar with math, it was pretty obvious that this was simply a dearrangement problem. And dearrangements are basically it's basically described by this problem statement. Like you have n items at n different positions, and the arrangements find the number of ways to arrange the n items so that none of them start at their starting position. So basically, how do you find the arrangements using in a program? Is basically using complementary counting, where you find the total number of ways to arrange. You find number of ways to arrange total minus the number of ways that are invalid. And invalid means that there's at least one position where it has its starting candy. So how do you do this? So the total number of ways is simply n factorial, because that's the total number of permutations of n items. Number invalid. So here we do some math. We define x of k to be the set of permutations that has the candy originally at k still at position k after the permutation. And so the number of invalid is the size of the set of x1 union x2 union x3, and then so on. And then so basically, how do you find this union? You need to do principle of inclusion exclusion with each of these sets. And principle of inclusion and exclusion is something that basically it calculates this expression. And you can honestly just memorize the formula. You don't really need to know the reasoning behind it. So basically, this is equal to x of 1 plus x of 2 plus x of 3. I'll assume we only have 3 right here. Minus x of 1 intersection x of 2, and then you do this 3 times, and then plus x intersection x of 2 intersection x of 3. And this is basically the formula to calculate the this union. This is called principle of inclusion exclusion. And so yeah, basically we implement this this formula. So here I already set up the input. So in this problem we need to find things with mod. So I'll type out the mod. Max is the maximum size that n can be. Factorial stores at each index A factorial. And finally, inverse stores that each index A, the number you have to multiply by in order to invert x factorial. And in order to find the inverse array, we need to use exponentiation. And this is the method. I don't know if you guys know this, how this works, but I'll go over it briefly. So this returns a to the power b mod, whatever mod is here. And then basically, I'll run through this method. If equals 0, that means it's a to the power 0. Anything to the power 0 is 1, so you return 1. Otherwise, you do the power a to the power of b over 2, and then you square that. So basically, this right now is a to the power of b. But if b is odd, b divided by 2 cuts off a 1, so you need to multiply by the base one more time to adjust, and then you return the power. And the time complexity of this is log b, because every time you call a method in this recursion, it halves it, so it's just log 2 of b. And we use that to calculate the inverse. So I'll first deal with calculating these two arrays. So factorial 0 equals 1, and inverse of that is just 1. And then we calculate it for rest of the indices. So the factorial, this part is pretty obvious. You just multiply by the number. And this represents a minus 1 factorial. So obviously a factorial equals a minus 1 factorial times a. So this part should be obvious. Inverse of a number x is equal to x to the power of mod minus 2 when the mod is prime, and 10 to the power of 9 plus 7 is prime, so you can use that. And I'll just write down the definition of inverse. Given x to the, its inverse is the number such that x times x to the power negative 1. This is the x to the, I'm using this to denote the inverse, is equivalent to 1 mod. We'll see how we use this later. So now we finally read in the input, read in the one line of input with n. And then we now keep do the complementary counting. Number satisfied counts the number that stays the same, aka the number that is invalid in the problem. And basically it stores this value. So then we loop through all the different number of scenarios where like A represents the variable A represents the number of indices that remain the same. And you notice from this following formula that you have a positive sign whenever there's an odd number of elements. So if A % of 2, meaning the number of elements that stay the same is odd, then you need to add it to the sum. And so what do you add here? So we want to calculate, for instance, for the very first one, we want to calculate this quantity. So suppose like K stays the same. Suppose so we know A stays the same. So so N choose A is the number of ways to choose is the number of these. So for instance, N here is 3, N choose 1 equals 3, and that's why there are 3 terms right here. So we first do N choose A. N choose A is N, the formula for that you just memorized is N factorial times divided by A factorial. And the division here, division modular arithmetic is just equivalent to multiplying by the inverse, which we already calculated earlier. So it's just N factorial divided by A factorial times divided by N minus A factorial. That's just a formula you need to memorize. Yeah. And then after that, so we've chosen the indexes that stay the same, but we also need to consider the under indexes, and there are N minus A of them, and there's so there's N minus A factorial ways to shuffle them up. So we just multiply it by factorial of N minus A. Notice that you can just delete these two since these cancel out, but I just wrote this out just to like show my reasoning. And then for this, instead of adding, you just subtract, because you set the signs alternate. This is positive, negative, positive. And yeah, here you just subtract instead. And then at the end, you just print out the answer. And remember, we did complementary counting, so don't forget to subtract it from the total number of ways, which we right here said was N factorial. So N factorial minus number that are invalid, and then we print that out. Should have no errors. Okay. Right. Okay, so this was right.
So
does anyone have any questions?
Yeah, so why is multiplying by the modular inverse the same as like dividing by the number?
Because so when you divide by a number, let me crop this. Okay, so when you division by x, so when you're dividing by x, you are in fact just multiplying by 1 over x. And 1 over x when it comes to modular arithmetic is just a modular inverse. Because basically, suppose you like x times the modular inverse y, let's call the modular inverse of x, y should be equal to 1, right? Because this is what happens when you do x times 1 over x, which is what you want to do, equals to 1. So we define the modular inverse to be the number that results in this. And it just happens that like it's a math thing that y, and when the when the mod is prime, it's just the number x to the power of mod over mod minus 2. Does that answer your question?
Yeah.
Okay. Okay, so I'll just hand it over to Andrew, I think.